Hello, everybody. Welcome to Weekend AIP Open Seminar today. So before starting, here are some important notices about this seminar. So reproduction is prohibited. Reproducing all or any parts of the contents is prohibited without the author's permission. This seminar will be recorded and the video will be available on the Weekend AIP website later. And during the talk, if you have any questions or comments, please use the Q&A button. You can write your comments here. Okay, so then let's start. So this is the seventh AIP Open Seminar, and my name is Masashi Sugiyama. I'm team leader of the team called Imperfect Information Learning Team. So in the beginning, I give an overview of our team. And before starting, let me briefly talk about Weekend Center for AIP itself. So Weekend AIP is a 10-year national project in Japan, started in the year 2016. So this is the 4th year. And we have 5 missions in the center. The first mission is to develop next generation AI technology, like learning theory and optimization theory, algorithms, etc. Then the second challenge is to accelerate scientific research by AI, like material science, cancer research, stem cell research, genomics, and etc. And the third challenge is to contribute to solving socially critical problems, like natural disasters or elderly healthcare. Then the fourth issue is to study ethical, legal, and social issues of AI. So nowadays, these are quite important, like ethical guidelines of AI, privacy protection, etc. Then finally, to grow the AI community more, we try to contribute to human resource development in this field. And so far we have hired many researchers and also students, and also we invited many interns and visiting scientists. And we have more than 40 industry projects in the center. And our team, Imperfect Information Learning Team, is contained in this first issue, so developing next generation AI technology. And our team consists of 3 researchers now. So Ganyu, Vut Tankarat, and Shuo Chen. So they will give talks later. And previously we had 2 more postdocs, Miao Xu and Bo Han. So now they are faculty members in Australia and Hong Kong. And I should note that so our team is supported by many great visiting scientists, junior research associates, part-timers, and also interns over the world. So their contributions are really, really significant in our team. And the aim of our research is as follows. So in supervised learning, collecting labels is often very expensive or sometimes very difficult or even impossible. So we try to develop machine learning methods that can learn from imperfect information. So that's the main challenge of our team. And more specifically, we are working on several topics like weakly supervised learning, noise robust learning, adversarial learning, transfer learning, metric representation learning, and reinforcement and imitation learning, etc. Today, I will give a brief overview of our weekly supervised learning research, and then later I switch the microphone to other research members in the team. Okay, let's start from the first topic, weekly supervised learning. In ordinary supervised learning, so we need fully labeled data. Fully labeled means input-output pairs, like positive samples and negative samples in the case of binary classification. But collecting fully labeled data can be expensive in practice or sometimes impossible in some applications. So then our question is, so can we utilize weakly labeled data? So that's the challenge of weekly supervised learning research. And we consider various different weekly supervised learning problems and give solutions. The first setting is called PU classification. Here, P means positive and U means unlabeled. So PU classification means we only have positive data, like blue data here, and unlabeled data, black points here. But still, we want to separate positive data and negative data. Actually, so there are negative data in the right-hand side, but we don't have any training data from the negative class. So this kind of PU classification happens in many real-world problems. For example, let's consider click prediction. So suppose users see a certain advertisement on the web page, and we want to predict whether that user want to click this advertisement or not. And actually, it's easy to collect positive data by just taking the log of clicked advertisement. So that's straightforward. Then what about negative data? So it seems like just collecting advertisements that were not clicked. But unfortunately, those unclicked advertisements are not really negative data, but they are either positives or negatives. Like, for example, if users don't like those advertisements, then right, okay, they don't want to click them. So they are negative advertisements. But sometimes users like those advertisements, but they don't have time to click them. Then those advertisements are not clicked. So in that case, unlabeled data are actually positive data. So that means in this scenario, we can only collect positive and unlabeled data. But finally, we want to classify the samples into the positive and negative class. So that's the setup of PU classification. But the goal of learning is quite the same. So we try to minimize the risk of a classifier. Like, I don't really go into the technical detail today, but we consider sample X and classifier F and output Y, and L is a loss function. And this point-wise loss is expected over all data points. So that's the standard definition of the classification risk. But we want to estimate this classification risk only from positive and unlabeled data. Actually, if we have positive and negative data, estimating the risk is straightforward because we have only expectation over positive data here and expectation over negative data here. And those expectations are simply approximated by sample averages. But in this PU classification scenario, we don't have positive data and we don't have negative data. So then approximating the second expectation here. So this is not straightforward. So that's a technical challenge here. Then actually this problem can be solved in a very simple way. So we use unlabeled data. So by definition, unlabeled data is a mixture of positive data and negative data. Unlabeled density is a mixture of positive density and negative density. So by equation, so P of X, so this is unlabeled data density. So this is a mixture of positive data density and negative data density. Like the blue one is positive density and red one is negative density. And unlabeled data densities, they are mixtures like this. By using this equation, we can basically eliminate the expectation over negative data. So basically by moving this term to the left-hand side. So we have P minus Px given y equals +1 here. Then so everything is straightforward. We can now approximate this classification risk only from positive data and unlabeled data. Then standard empirical risk minimization is possible only from PU data. And we can also similarly have an estimation error bound like this. So this is a kind of optimal convergence rate, and we can really solve the problem of PU classification in a nice way. So that's a very good result. Then based on this result, we can actually also solve a semi-supervised classification problem in a nicer way. We call it PNU classification because semi-supervised classification basically uses positive, negative, and unlabeled data. So that's why I call it PNU here. So it's like this. We have all blue and red and black points here. And our idea is to decompose this PNU problem into PU, PN, and NU problems. So each sample appears twice, but this is fine. And already I have shown in the previous slide, the PU classification problem can be solved in a nice way. Then NU classification problem. So this is essentially the same as PU classification, but just the label is flipped. So we can also solve NU classification in a nice way. Then finally, PN is a standard supervised classification problem. So we can, of course, solve it in a nice way. Then altogether, so we can solve all three problems in a nice way. And our idea is to just linear combine those learning criteria and minimize them simultaneously. Then surprisingly, so we can show that the minimizer actually achieves a very nice generalization performance. And I don't really go into the technical detail, but we have an order of 1 over square root of NU. So NU is the number of unlabeled data. So this means that under some reasonable assumptions, if we have many unlabeled data points, we can really reduce the generalization error. So that's a very nice, surprising result. Then, okay, in PU classification, we used positive and unlabeled data. But now let's go further into weaker supervision. So that's basically P classification. So we want to train a classifier only from P data. This kind of situation often happens in reality. For example, if we analyze the company data, then so we can collect data from our own company, but we are not allowed to access the database of rival companies because of some privacy reasons. So in that case, we can only access P data and not N data and even U data. But unfortunately, only P learning is not possible because it is basically unsupervised learning, unsupervised classification, or one class classification. So there's no way to really evaluate that generalization. But we found that if the positive data is equipped with confidence, we call it positive confidence or PConf, then empirical risk minimization is possible. So again, I can't really go into the technical detail today, but we can re-express the risk function in this way. So R is the positive confidence. So it's basically the probability of having the positive class. So basically, we augment the positive data with negative data like this. So R and 1 minus R. Then apply importance sampling from positive distribution to unlabeled distribution. Then in the end, we have this expression of the risk. And we can naively apply the empirical risk minimization because we only have expectation over positive data and confidence values in the equation. Again, so we have nice estimation error bound, and that converges in the order of 1 over square root of n. So this is the same order as standard supervised classification. So that's theoretically optimal. Then let's go further into weaker supervision. So this is maybe the weakest supervision. So we call it UU classification. So UU means so unlabeled. So we are given 2 sets of unlabeled data, like this one and this one. And each unlabeled data set contains some positive samples and negative samples here and there. And we assume that their class pairs are different. So class pair means so their balance, positive, negative balance. Maybe in the left-hand side, so we have, let's say, 50% positive points and 50% negative points. But in the right-hand side, let's say 80% positive and 20% negative, and things like that. Then surprisingly, only from 2 sets of unlabeled data, we can train a classifier in a theoretically optimal way. So again, with the estimation error converging to 1 over square root of n. So only from unlabeled data, 2 sets of unlabeled data, we can really train a classifier that separates 2 classes. And technically, so in PU learning, we regarded unlabeled data as noisy negative data. So that was the trick behind PU classification. And in a sense, the UU classification is an extension of PU learning. So now P data is also negative, or also noisy. So then we use actually noisy positive data and noisy negative data. So in a sense, one set of data is regarded as noisy positive, and the other set is regarded as noisy negative. And we try to train a classifier only from noisy, positive and negative data points. So that's the key idea of UU classification. So that's a very general solution. Then as a special case of UU classification, we have an interesting example. It's called SU classification. So S is similar data pairs. So let's consider some delicate classification problem, like about your salary or about your political opinion or religious belief or something like that. And in that case, it's actually highly hesitant to directly answer questions like, is your salary rather than like $100,000 per year or something like that? So nobody wants to really answer those direct questions. But sometimes it's easier to answer like, okay, my answer is same as that person or same as another person or something like that. So in that case, like two samples, we know two samples belong to the same class. Like these two samples belong to the same class, but we don't know whether they belong to the positive class or negative class. So that's similar data pairs. And we found that only from similar data pairs and unlabeled data, we can train the classifier again. Actually, mathematically, this formulation is regarded as a special case of UU classification by decoupling the S pairs into unlabeled data. Then we have actually two different unlabeled data sets, and we can apply UU classification. And we can actually further extend this method to handle dissimilar data pairs. Like my opinion is different from that person. Like this point and this point belong to different classes, like that. Then DU classification is possible. Then now SU and DU classification are possible. Then SDU classification is also possible in the same way as PNU classification. So that's a very general framework again. Then let's jump into a multi-class situation. So now we have more than two classes, let's say 3 classes or even 100 to 1000 classes. And if we have many classes, actually labeling is quite costly. Like suppose we have 1000 classes and we use crowdsourcing to label the image. Then, okay, we have a list of 1000 class labels and we need to find the right answer from this long list. So this is really time consuming and painful. So our idea is to give up collecting correct label, but we rather use wrong labels. So that we call complementary labels. So more specifically, so a complementary label specifies a class that a pattern does not belong to. Like usually, so we say this pattern belongs to class 1, or this image contains dog and something like that. But complementary label is a not label. So this pattern is not class 2. This image does not contain airplane or something like that. And actually collecting such complementary labels is much easier and cheaper than collecting ordinary labels. Because if you have 1000 classes and only one is correct, then if you just randomly pick one of the classes, then this is almost always incorrect. And we just select it and confirm that this is wrong. That's it. So it's much faster and easier. And we have shown that only from complementarily labeled data, we can again train the classifier by empirical risk minimization. And again, the convergence rate is 1/n. So it's a bit surprising because complementary labels is much weaker than ordinary label, but still we can achieve the same convergence rate. And technically, so noisy labels with uniform transition to other classes is the way to solve this problem. But today I don't really go into the technical detail, but we can have a very simple solution to this problem. Once we have complementary label classification problem, then actually we can improve the labeling process in a simpler way. Like instead of asking multi-class labeling question, like please choose the correct label from like a list of from a long list of labels, but we can just use yes/no question. Like we just select one of the samples randomly and ask the crowd worker, so is this SoftBank pepper? So in this case, actually, the answer is yes. Then this sample is recorded as an ordinary label. So that's really a golden standard, precious one. But for this image, if we ask, is this iRobot Roomba? Then the answer is actually no in this case. Then usually, so such a no label was regarded as just useless and they were thrown away. But based on our complementary classification research, we know that complementary labels also contain precious information, and we record it as complementary label, and we can actually improve the performance. Then in the end, we use both of them. So we consider the risk estimated from ordinary label data, and also risk estimated from complementary label data altogether. Then we can actually systematically improve the classification performance. Then finally, let's consider another problem called partial label classification. Actually, the concept of partial labels was studied already more than 10 years. And a partial label is a subset of labels that contain the true one. This means so either class 1 or class 2, or this image contains dog or cat, or something like that. You can have multiple label candidates, and one should be correct. So this partial label is also easier to collect because we don't really have to choose the right one, only single one, but we just select roughly some candidates. And at least if we can guarantee that the correct one is included in this candidate, then that's fine. And actually, complementary labels are a special case of partial labels. And partial label classification is a more generalized version. And we can also kind of extend the complementary classification approach to partial label. And we have a theoretically, solid approach to partial label classification. Okay, that was a brief overview of weakly supervised learning methods we have developed in the last couple of years. And let me summarize the talk. So this is a kind of map of weakly supervised learning world. So I took the labeling cost on the vertical axis, so high and low. Then the classification accuracy on the horizontal axis, low and high. Then supervised classification is actually quite accurate. So it is located on the right-hand side, but it requires high labeling cost. We need all label data. So it's actually most expensive. So it's located on the top right corner of the illustration of the graph here. Then unsupervised classification. So it does not require any labels. So its labeling cost is actually 0. So it's minimum. But unfortunately, so it cannot be really used as a supervised classification method because there's no guarantee. So it's located on the bottom left corner, like here. Then standard semi-supervised classification. So we use some label data in addition to many unlabeled data. And we wanted this to be much brighter than here. But unfortunately, so traditional methods requires so-called some smoothness assumptions, like cluster assumptions or graph adaptation smoothness and something like that. Then, so it does not always work well in practice. So it is relatively located on left-hand side. So in a sense, our research tried to explore this bottom right corner. So now we can train a classifier systematically from some weakly supervised data. And actually, all approaches I explained today are basically estimating the risk, classification risk from weakly supervised data. So then actually all of them can be combined in a systematic way. So that means we can actually have a PNU, PConf, NConf, ST, conf partial classification or something like that. So this is possible as long as we have weakly supervised data from many different sources. We can actually combine them. So it's a kind of nice systematic framework for handling weakly supervised data. And now we are writing a book on this machine learning from weak supervision. And originally, this book was supposed to be published within this year, but unfortunately, due to this corona pandemic, the process is a bit slower, and hopefully we can publish it in early next year. Okay, so then this is the last slide. So this is a kind of conceptual idea of our research on weakly supervised learning and more in our team. So we try to decompose machine learning research into the model axis and learning method axis. And model axis is a kind of popular direction, like starting from linear model long time ago. People try to make it non-linear, but still easy to handle, like additive model or kernel model and deep model. Now the model is getting deeper and deeper and more complex and more complex. So many application people are kind of designing suitable architecture for their problems. So that's the model research. And our research is basically orthogonal to that model direction. So learning method is basically orthogonal. Like we can consider supervised learning for any models and unsupervised learning method for any model, then semi-supervised, weakly supervised. And we can also consider reinforcement learning, transfer learning, adversarial training, noise robust training, etc. So we are kind of exploring this direction, learning method. And in the beginning, so this research, so learning method research can be independent of model research. So we can completely separate them and study just the properties of learning method. This is what I explained today. But in the future, we may also combine these two. Like if we focus on deep learning, deep model, then we have many interesting properties. And I think the next speakers will also talk about some nice ideas. But then we can more kind of customize our learning method to particular models, like deep neural networks. This is what currently we are exploring. Okay, so then this is the last slide of my talk, and thank you very much. I had several questions on the chat window and also QA box. So let me start from this question. Are there assumptions on the type of the classifier? So I already answered your question here. So our methods, all of our methods are basically like model agnostic. You can basically use whatever model as long as it is expressed as f of x. Then the second question is, it seems the SU classification could be used on the superpixel. So in the case of superpixel, it's a set of X. So I can't really answer your question directly because the formulation is not exactly the same. But yeah, let's see. So if we can really formulate the problem, superpixel problem into binary classification on single sample, then so we can apply, maybe we can apply SU classification. But maybe we should study a bit more about this. Then we had two more questions. So the so-called complementary label is widely existed in the medical report, which usually causes much trouble. Oh, that's great news. Thank you very much. Then we should definitely use that knowledge, that information. I think previously those complementary information was regarded as just noisy and useless. But actually, we can really obtain information from those complementary labels. We should definitely use that. And this solution seems a perfect solution. No, thank you very much. That's great. And I had one more question. So UU learning is close to unsupervised learning since there are no any labels. Is UU considered as weakly supervised learning? That's a very good question. And yes, it's basically unsupervised because we don't have any single label. But still, we can solve a supervised learning problem. So that's the difference from standard unsupervised learning. But it's not completely unsupervised because we need some assumption on unlabeled data. So we have two sets of unlabeled data with different classifiers. So that's a bit stronger assumption in some cases. But it's not completely unsupervised, but it's much closer to unsupervised. And that's why I still call it weakly supervised learning. And we had one more question. Is that possible to consider more complex data, such as interval data? The observations are interval-like data, not real number-based data. That's a very good question. So I think this is, again, another orthogonal direction to like weakly supervised learning. Like for supervised learning, we have already several research on like learning on interval data. And basically, we just tried, then we should extend that research into weakly supervised direction. So that might be something we can consider. Yeah, I think that's still open and this combination is still possible. Then one more question at the end. So is weakly supervised learning close to missing data analysis? That's a very good question. So in a sense, missing data analysis is also a kind of weakly supervised learning or imperfect supervision. So in a sense, missing in which way? So that's the question. For example, in PU classification, so we miss negative data. So that's a kind of missing data. But usually, if you say missing data, then we have a vector input X and some elements are missing or something like that. So that is a bit different from current weakly supervised learning formulation that we have explored so far. But this is definitely very interesting. And it's actually somewhat related to the previous question, interval data. So interval data is also like X is not a 1 point, but it exists in a certain range. So missing data is a kind of special case that the range is infinity for some element. Yeah, so again, this is a bit orthogonal to the current direction. And yeah, I believe it is possible to combine some of the missing data analysis techniques with our weakly supervised learning formulation. Okay, thank you very much. So this is the last question and I finished my talk now. Then let me introduce the next speakers. So next speaker is Gan New. So he's a research scientist in our team. And his talk is about robust learning against label noise. Then after that, Wood Tankarat, he's a postdoc in our team. He talks about sequential decision-making from noisy demonstrations. Then finally, Shuo Chen. So he's actually a new member in our team. So he's a postdoc. So he will talk about robust distance metric learning. Okay, then so Gan, so would you start your talk?
Okay, then I will start. Okay, this is the outline of my talk today. I'll first introduce the problem setting and some very high-level approach to correct noisy labels, and then I will talk about loss correction and sample selection and some extensions. Okay, we all know that machine learning is the science of data. When we talk in this talk, we focus on supervised learning, such as the classification, where the data look like the input and output pair, where the output is called a teacher or supervisor. So typically supervised learning means that the output is somehow not very reliable in some sense. For example, we can have incomplete supervision. Basically, it's sample-based learning or similar from settings where we have very limited label data plus a huge set of unlabeled data. This was already introduced by Professor Sugiyama. I focused on this line when I was at Tokyo Tech, Baidu, and University of Tokyo. Then after I joined Lincoln 3 years ago, I focused on inaccurate supervision. This means some outputs can be incorrect for some inputs. But we don't know which outputs are incorrect, so we want to identify them or systematically correct them. There are also inexact supervision. This means all inputs and all outputs are grouped into bags like multi-instance learning and partial label learning. I will selectively talk about this in the last slide. Okay, the title is Weekly Super Deep Learning. So we also want to take into account deep learning or representation learning. So how to nicely combine weekly supervised learning and deep learning is the key issue, because deep learning and deep models and linear models have some very different properties when training. Okay, let me introduce deep learning and label noise. What we have is a data set for training. We denote it by xi and y tilde I. S is drawn from some unknown corrupted drawn distribution. So the data generation process is from x to y, and the label correction process is from y to y tilde. There are some key observations, like we only corrupt the class posterior probability, and x is the root in this process. So px remains the same. This is very important to design some sample selection or label correction methods. Also, py tilde is determined once py tilde given x is fixed. This is basically makes things easier for analysis, but this is not used in algorithm design. So what we want is a deep model to robustly classify future data drawn from the original pxy. Why we want deep model, or why this is difficult? Because linear models are poor on complex data, so they can only handle some tabular data or some low-dimensional data where we can use a Gaussian kernel or other kernel model. It's due to approximation error. On the other hand, the deep models are poor under label noise because the model capacity is very high, so it can fit everything. Deep model is especially very sensitive to the label noise. Okay, this model is called class conditional noise. This is the most popular noise model, and maybe I think if you can find 10 papers, more than 9 papers will use this model in their experiment and algorithm design. So how can we define this model? Due to the law of total probability, we can express this corrupted class posterior probability in this way. And then we assume that this corruption is instance independent and class conditional, namely the py tilde given xy equals py tilde given y. Equivalently, we can express this process using a transition matrix where the ijth element is the probability of corrupting from the S class to jth class. Then we can write the whole process, corrupting process, into a more compact manner. Like this is a vector of the corrupted class posterior P vector given X, and we use this transition matrix to corrupt this one, the clean vector. Okay, let me show you. This is not very clear. Okay, let me show you some toy example. So in the left, we have the rational clean training data. We can see that we have two components in this Gaussian mixture model, and we use color to denote class, and all the four classes are well separated. This is easy to optimize and easy to generalize. And then we corrupt half of the training data uniformly to other three classes. You can still see that like a red and green, yellow, blue, the original class dominates this one because we corrupt half data. But now it's very hard for the machine learning model to generalize to this one. Yeah, it's easy to, somehow if we use deep model, it's still easy to optimize, but it's very hard to generalize. Okay, so here I give you some real world example to the crowdsourcing and search engine. So I think the noise labels are almost everywhere in practice. Sometimes we use active label collection. We use some crowdsourcing platform to collect some data because the labels are from the non-experts, so they contain certain noise. Okay, a difference here is that in dealing with noise labels, for every data point X, we have only one label. So we cannot use some label aggregation like in crowdsourcing to obtain more reliable label for a single data point. Also, this is passive label collection. Sometimes we regard the user click, the user behavior as the supervision, but we cannot guarantee that people always click something really relevant to the search. This is somehow already explained by Professor Sugiyama in the last talk. So I will skip this. Okay, basically, this slide is the most important one in my talk. We can divide existing methods into three approaches. Loss correction, we want to design a corrected loss function such that if we can minimize the corrected loss on noisy data, it's equivalent to minimizing the original loss on clean data. Then we have sample selection and reweighting. So in sample selection, we just want to select the data that look like the correct data, and then we train only on the selected data. And we can similarly have reweighting. Basically, we upweight and downweight the data if they look like correct or incorrect. So we have finally we have label correction. In label correction, we somehow correct the labels using correct given labels using predicted labels on the fly. But this one doesn't work very well. So recently in ICTL this year, we have a paper called divide mix. It's a huge family of algorithm now. We use indirect label correction. So we first do sample selection. We select some correct data, and then we just drop the label of the unselected data. We regard them as unlabeled data, and then we perform sample size loading. This one can perform some indirect label correction, and this one works very well in practice. Okay, next. Let me check if there are. Oh no. Sorry. Okay, maybe in the end I will check whether there are some questions. So, okay, let me briefly introduce empirical risk minimization. We just want to minimize the classification risk defined as the loss of GXY on the clean distribution. So we use training data to approximate this one, but this only works in supervised learning. When we have label noise, we don't have any data drawn from PXY, so we cannot use this. Basically, we have two main methods for correct the loss. Okay, let me skip the technical detail. We just need to know that backward correction is risk consistent. It reverses the label correction for any classifier and the loss. And the forward correction works better. It's classifier consistent. Basically, we use this as the correct loss. Previously, we have the loss. Some, for example, cross entropy is on Gx and y tilde, and here we multiply Gx using T transpose, and then we still use the cross entropy loss on this one. Intuitively, it's like because we have some corrupted, some noisy labels. So after we get the softmax output of the classifier, suppose it's clean, we use the same corruption process on the softmax on the predicted class posterior, and then we basically match the corrupted prediction and the corrupted noise labels. This guarantees to find the clean py given x. So forward correction simulates label correction for probabilistic classifier and loss. In practice, we implement this by insert a noise adaptation layer between softmax and cross entropy. We have two choices, like you can use pipeline, the first estimate T, and then train the classifier based on the estimate T. But this is too restrictive. We can also try end-to-end. We train T transpose J as a whole without really estimating T. This is too flexible and suffer from the optimization itself become difficult. We have three ideas in improving the loss correction. First is masking. We have an end-to-end solution, but with structure constraints. Masking use masks, like in this figure, this mask, the black one. Human cognition will mask invalid transition. That means we don't allow the class I to be corrupted to class J if it's black. And then learning algorithm can then take care of the black entries. Thus, the burden of the training could be remarkably reduced. Okay, by using this mask, we can easily incorporate any prior knowledge about the structure of T. Then technically, how to align T with values to a structure without values, because these masks only say whether Tij is 0 or Tij is positive, but without any value. So we give every structure consistency a chance, and we use Bayesian inference to learn the classifier. Okay, next we have T revision. Basically, this pipeline solution, but we have end-to-end revision. I need to first explain what is anchor point. So X is the anchor point for class I if we have this the probability of X belonging to class I equals 1. Then given anchor point for class I, basically we can, under the probability of the corrupted class, we can recover a column of the transition matrix T. And also when X is the anchor point and we don't know it is the anchor point for each class, it's very easy to solve this. We can just take argmax of the py tilde given X, and then we can find it is anchor point for which class, because T is diagonally dominant. Then we consider without anchor points. For example, we can have some data point where this is not 1, but close to 1. Then we cannot accurately estimate T. So our solution is that we first fit noisy training data to have this py tilde given X, and we find data with highest p hat y tilde given X. This is very important step. And then we estimate T from likely anchor point, and we just train G based on T hat. The first and the second step are regarded as some iteration. And then we repeat the following step. We revise T hat and update the classifier, and then we revise T hat and update classifier until this classifier converge on noisy validation data. Okay, the whole thing is in this figure. Previously is T transpose G, but here we have T hat plus delta T, and every time we just modify this delta T. Okay, so I have introduced the two approach. Here I want to directly focus on how to reduce the estimation error of T hat. We think that the bottleneck is how to estimate py tilde given X. It's because py tilde given X has larger conditional entropy than py given X. So usually the p height of y tilde given x will have larger estimation error. Please see this figure. The x-axis is the sample size in logarithmic scale, and the y-axis is the estimation error. So this green line is the error for clean class posterior, and this blue and orange line are the estimation error of the symmetric 20% symmetrical noise and 45% pair noise. We can see that it is much harder to fit this p height given y tilde given x than p height y given x. So how to solve this? We introduce y prime and factorize the t into the t spade and the t club. We can see that one class encodes the transition from y to y prime, and the other encodes transition from y prime to y tilde. Okay, it seems to be transformed the problem into a harder problem, because now we need to estimate two transition matrices. But if we carefully choose the intermediate class y tilde to guarantee that sorry, py prime given x equals p height y tilde given x, then we can obtain the first estimate using anchor points, and it has no estimation error because we have exactly this term. And then in order to obtain the second transition matrix, we use sampling and counting, because we define the intermediate class y prime in this way. And we have this p height at hand, so we can generate as many samples as we want, and then we can count very accurately. Its estimation error can decay exponentially. Then under mild conditions, we can guarantee that if we estimate these two separately and then times them together, we can guarantee some smaller estimation error of t. Okay, I have finished the loss correction approach. How much time I have? Sorry, I will quickly go through the sample selection approach. In this part, we want to identify the correct training data. We use loss as a criterion. Suppose that we have G trained on clean data and we fit noisy training data through G. We will find that small loss data will be approximately correct data, and the large loss data will be approximately incorrect data. However, we don't have any clean data to train G to identify the correct data. The key point is that the memorization deep network can help. While deep networks can fit everything due to the large model capacity, they learn pattern first. Look at this figure, where the blue curve stands the accuracy on correct training data, and the red curve stands on the accuracy on incorrect data, and the purple curve is the accuracy on correct test data. We can see that clearly said that deep DNA learn pattern first. And we use this property to design self-teaching. We just during training, we regard small loss data as correct. And this one maintains a single deep network. But we know that small loss data are likely but not certainly to be correct. So this one can get some error to propagate in later epochs that in fact training. So our ideas have co-teaching and co-teaching plus square and S2E. Let me briefly go into this. Co-teaching maintains two deep networks. So in the forward pass, we feed forward all the data in the mini batch by two networks, and then we select a small loss data by the two networks. But after, when we back propagate data, we just propagate dB by A and dA by B, like shown in this one. So when a mislabeled data is selected by A, why co-teaching works? We can see that B may fix this mistake of A, and B may reduce its influence. And when it reduces the inference, it could delay its inference, because when A meets the same mislabeled data in the next epoch, in self-teaching, A has already memorized it. So A will make the same mistake once more. In co-teaching, A has not memorized, so long as B has not selected in the last time. The take-home message, the most important take-home message is that in sample selection, we should let a network only learn from others. We can memorize others' mistake, but we should not directly learn from our own experience. In order to avoid to memorize our own mistake, because if we memorize our own mistake, we will repeatedly make the same mistake again and again. Okay, the essence of co-teaching plus is that how to keep the two networks sufficiently different, because if they are same, we will degenerate into self-teaching. We use a method to first after we feed forward all the data, we first find a subset of data on which the two networks, the prediction disagree with each other, and then we just run similar things like co-teaching. Okay, this is the method improving self-teaching. It also maintains a single network. But the motivation here is deep networks cannot easily forget bad data once they are memorized. So we propose something like we will integrate a stochastic gradient ascent into SGD. So we will perform SGD on good data as usual, and we will perform SGA on bad data with reduced learning rate, where the goodness or badness is respect to the base learning algorithm. For example, in self-teaching, small loss data are regarded as good data, and in backward correction, the non-negative loss data are regarded as correct. So basically, this square is a special design realization by pulling optimization back for generalization. We can see that the left is the stop grad and the right is square. We can see that if we only do stop grad, we cannot easily forget the bad data after it is learned. But in this one, after we perfectly learn the good data and the bad data, but after that, if we perform stochastic gradient ascent, we can ask the network to actively forget the bad training data. Okay, finally, in this part, I will introduce searching to exploit, because there is the open question, how many small loss data to select in a mini batch of AIP of T? The speed of memorization depends on so many factors, like the data, the network, and the optimizer. So intuitively, a good selection schedule will satisfy that in the beginning, we select all the data, because the independent first, and then we first decrease and then keep it flat or increase. But we don't know when should we decrease and when we should turn to flat or increase. And when we decrease, to which point should we decrease? Should we decrease to the noise rate or significantly lower than the noise rate? We propose to search for the selection schedule rather than manually design it. The base learning algorithm is just a co-teaching. And the meta-learning algorithm is on validation data, we fix the trained network and search for better RT, where RT is modeled by some basis function and optimized by Newton's method. Okay, we can see that this green line was the manually designed RT selection schedule in previous papers, and these purple lines are learned. They look very different. Okay, this is the final slide of my talk. It's extension. I have introduced the loss correction approach and the sample selection approach. I didn't introduce label correction approach because the underlying assumptions are quite similar to sample selection approach. Just the technical details are different. If you want to do CCN research, it's already red ocean. I recommend you to consider instance-dependent label noise. Instance-dependent label noise, where this T is no longer a matrix, but it's a matrix value of the function T of X. We have some paper in this direction. This is somehow very difficult because Tx is not identifiable. So we need to put some more assumption, like the noise is part dependent, or the noise is difficulty dependent. Then we can consider learning with corrupted Px given y, like shown in this equation. This is very difficult. We have the causality is reversed. We have y tilde to y to x, and it's a model for sampling rather than labeling. And here, PX can be different, and the p-value tutor is free. We need to specify a p-value tutor in order to sample X. So for this kind of problem, we can still use loss correction. But for sample selection and the label correction, maybe we cannot use them directly because there will be, say, obvious correct shift or some other like imbalance, class pair shift that will hurt those deep learning based method and the popularity code. So it's better to work on this area. Also for learning with partial labels. For learning with partial labels, it's noisy in another way. When we ask some non-expert to label our data, if we force them to select only one, then we get a noisy label. If we ask them, you can select as many as you want, but you must guarantee that the true label should be in the selected set, then we'll get a partial label. Okay, the problem settings are very different, but we can use similar techniques like label correction and loss correction to handle this one. So I recommend you to consider extension in this slide, and that's maybe it will be easier to publish paper in these three area. Okay, this is my last slide. I need to say QA. Okay, transition process of T is considered as one additional layer. The training end-to-end what assumption can be imposed on T. Okay, if it's fully end-to-end, there is no assumption. That is why we want to use masking. Like we put some constraint that only this white elements can have positive values. All the black elements must have zero values. Otherwise, it's too difficult to learn it. And could the noise be related to the uncertainty? So the noise level could be underestimated. I think your noise is difficult from my noise. Your noise means it's on a point, but label noise is something systematic. It's on the entire distribution. If you decompose it into each point, then of course it is related to uncertainty. Okay, in the instance independent noise part, basically we consider uncertainty because this is a very important assumption. Like let me show you. Like in this paper, and this confidence score make IDN learning possible. Confidence score basically means certainty. Okay, what is the major difference between co-teaching and knowledge distillation? Yeah, they are not really related. Co-teaching, okay, both of them extract some knowledge, but the purpose is different. Co-teaching want to manipulate the data, and the knowledge distillation want to manipulate the model. We want to compress the model so that we can compress the model into much smaller, but the performance is almost similar, just slightly worse than the previous one. It is for deploying to the mobile device or similar things. Okay, next question. Can correct shift method and same method combine to solve corruption? I guess so, but to be precise, it's not really correct shift. I mean px will change, but I don't mean p back given x will be same. Maybe this is not the original definition of correct shift. I'm sorry, I misused the term. Yes, if you combine something that can explicitly handle the change of px, and then you use the CCN to handle the change of py given x, maybe you can handle it. I'm not sure. We need to try. Okay, next question. What is the advantage of the sample selection method compared to label or loss correction method? Okay, the advantage is that you don't need to estimate T because estimating T is really the bottleneck. And you just need to know the noise rate, or sometimes you even don't need to know the noise rate. But but there is no free lunch. Label correction and the loss correction will use all the corrupted training data, but the sample selection will only use a subset of the training data, the correctly labeled one. If the noise rate is high, we will just throw away a lot of training data, which may be waste, because we know that PX does not change. So in the worst case, we can regard them as unlabeled data. Okay, are there any relation of noise labeling to adversarial learning? I think there should be some relation, but technically it's independent. When we corrupt Y and if we want to corrupt X, and especially in label noise, the Y is corrupted in the beginning and then fixed. But in adversarial learning, we want to corrupt X on the fly. And also in label noise learning, the test performance is still the accuracy or maybe FN score or AUC. But in adversarial learning, the test part is also the adversarial risk. It's no longer ERM. It's called adversarial ERM. I think that's a key difference. The test, the evaluation part depends on the model. Also, the last question, as for identification of correct training data, does the approach make deep learning perform smooth function approximation? In other words, where it is. In other words, can the method perform piecewise smooth function approximation? No. In identification of training data, we don't put any smoothness assumption. There are some paper in ICTL and SML, like the gradient clipping make the loss function smoother, and there are some it's called label smearing, which is a more general case than label smoothing. But the label correction and the sample selection, I say that their physiological motivation are similar, but the technical details are really different. Oh, there is a still question. In streaming data, the matrix T might change over time. Are there methods to adapt to estimate the matrix T over time? I think this is somehow related to instance dependent. You need to put a very strong assumption in order to guarantee that the T is identifiable. This is some interesting direction, but I don't know any paper working on this area. Okay, thank you. I think I need to stop.
So thank you very much. So let's switch to the next speaker. So Wood, can you share your screen?
Yes.
Okay, so let's go ahead.
Okay, so hello, I'm Wood Tankrat from AIP in the Imperfect Information Learning team. And in this presentation, my title is Sequentiation Making from Noisy Demonstration. So this is the outline one. The first one is the introduction. So one of the goals of AI is to design intelligent agents that makes sequence of decision to perform assigned tasks. For example, in the domestic tasks such as this iRobot Roomba, the task is to clean the floor. And we want the Roomba to make a sequence of parts to perfectly clean the floor. Another example is autonomous driving, where we want the car agent to make a sequence of parts to reach the desired destination autonomously. And for the future, we may have astronaut robot that can perform astronaut tasks like space exploration. And we want them to do this task automatically without human input. And in machine learning, we achieve this AI goal by solving sequential decision-making problems, or SDM. So the problem of sequential decision-making is to learn an agent that make a sequence of decision based on the environment state, so that it can achieve some goal. So we have agent on the left and we have environment, and these two interact by exchanging decision and state. And in this talk, we will focus on solving sequential decision-making from demonstration. So the standard problem of SDM from demonstration is, first we obtain good quality decision from expert. For example, in this figure, we have the goal, we have the task as to control the robot to reach the red object here. Then we ask expert to control this robot to collect this kind of expert demonstration where all of these decisions reach the make the robot reach the goal. And then in the second step, we want to train agent based on this demonstration to achieve the same task. Now in this presentation, we will focus on learning this decision making from noisy demonstration, where we have the same assigned task as to reach the goal, to reach the red object. But now we ask both expert and non-expert to perform this task. And after we collecting this data, we will obtain diverse quality demonstration, where some of the demonstration can reach the goal, where some of the demonstration cannot reach the goal. But we still want to train an agent to perform the task by imitating only the expert. So this is the theme of this talk. You want to learn from noisy demonstration. So let's go to problem formulation. So usually sequential decision-making problem is formulated as Markov decision process. So an MDP defines a discrete time stochastic control process, where it determines the interaction between an agent and the environment, which is an MDP. So in each time step, an agent that observes the state ST, we choose an action based on its policy pi. So we assume that pi is a conditional probability density of action given state. And the action is chosen by sampling from this policy. Then after the agent chooses an action, the MDP will sample the next state based on the state transition probability density PS. And it's also compute the reward RT based on the reward function R. Then the agent will observe this next state and the reward value. Then the time step will increase by 1, and this process will repeat until we reach the finite time step T. And after this interaction complete T time step, then we obtain a trajectory, which is a sequence of state, action, and reward. And the goal of Markov decision process is to find a policy that maximizes the expected cumulative discount reward, as shown in this first slide of the equation. So we have the reward function that is cumulative over time and discount by the gamma. And we want to find a policy that maximizes this expectation over the trajectory probability density, this phi as like this. And the policy that we obtain in this first slide will be equivalent to the policy we obtain in the second line based on by using the state action probability density. So it's basically just the probability that we observe some particular state action. So reinforcement learning is a very popular approach to solve Markov decision process by using sample that we drawn from P prime to update the policy. For example, we can use, if we have sample from P prime, then we can use gradient ascent to maximizing this expectation to obtain a locally optimal policy. And so far in the literature, we have seen many successful results of reinforcement learning, for example, in the AlphaGo. However, we have also seen some bad behavior of reinforcement learning, especially when we use some bad reward function. As in particular, in this work, they show that if we have some bad reward function, it's possible that the agent will hack this reward to obtain very high reward, but it does not finish the task. So in this example, we have a racing agent that the goal is to race with the other boat to reach the goal. And on the way, they can collect some extra item to increase the reward. However, what they observe in this task is that the agent can hack the reward by repeatedly collecting the item without reaching the goal. So it can obtain very high reward values, but it does not complete the race. So we don't want this. We don't want this behavior, but it happens. So this means that in practice, we need to carefully design a reward function to prevent such faulty behavior. However, in practice, it's very difficult to decide such reward function because we may not know if this reward function that we have can cause this behavior. So we need to try it, but in reality, we cannot try it because it's too unsafe. Also in autonomous driving, we cannot just let the car drive in the real world with bad reward function. So imitation learning is one way to avoid this issue by learning from demonstration. So formally in imitation learning, our goal is to learn a policy pi such that this policy is equivalent to the expert policy, which is denoted by pi e, or equivalently is the action distribution are the same. And what we have is a data set of state action that is drawn from this expert state action probability density. So if we have this data set, Then one popular way to learn the policy is generative adversarial imitation learning, or GAL. So GAL is very similar to GAN. So the goal of GAL is to learn a policy by reinforcement learning by using the reward that is learned from the discriminator. So if you are familiar with GANs, then it can be seen that this is basically GAN objectives, where we have the minimization over the generator, which is now denoted by pi, and maximization over the discriminator, which is still d. And this is a cross entropy loss. So the main difference between GAL and GAN is that in GAL, the data distribution will depend on the Markov vision process M. And when we update the generator, we need to collect the data from the MDP. So if we have expert data, then we can apply GAL and be happy. But now we will consider noisy demonstration where we have noisy data. So why we want to consider noisy data is because, as you know, in reality, it's difficult to collect expert data because expert can be very costly to collect data from. And even if they are expert, they can still make mistake during data collection. So the data that we have from expert may not be really expert data. So that means we should consider that the expert assumption that we assume so far does not hold. So we cannot assume that the state action that we have are drawn from the expert state action density. And in this presentation, I will present 3 algorithms that can robustly learn from noisy demonstration. So in the first work called Y, we use variational technique to learn the reward and the noise model. In the second work called ICTL, we improve the robustness of GAL by using the confidence scores. And in the last work called RealCode, we use classification rates to learn the policy robustly. So let's go into the first work, which is Y. So in Y, we make an assumption that noisy demonstration are generated based on the noisy action. So assume that we have a demonstration which is a sequence of state up to time t and sequence of action up to time t. Draw from this state action, draw from this trajectory distribution PD. And this PD is defined like this. So this is basically the same as the state equivalent is the same as the trajectory distribution defined in the previous slide, except that now we have these extra terms. So pi star is the optimal policy that we want to learn. And A is the optimal action that we draw from this optimal policy. Meanwhile, this Pn is the noise distribution where we observe the noisy action from. So now what we observe in this data set that we have is the noisy action. And this Pn will determine the expertise of each worker, where we have K worker, and for each K we have different noise distribution. So if this particular worker draw sample U that are similar to A, then we assume that this worker is very expertise and we should learn from them. And this is published, this work is published in ICML. So I will skip most details, so please see the paper for detail. But now the key idea of this work is we want to jointly learn the model of the reward and the noise distribution by this parameterized model. So this model is very similar to this data distribution, except that we replace this pi star by this exponential reward and replace this Pn by some Gaussian distribution. So basically we want to learn a reward function such that the product of this reward is proportional to the product of the policy, so it's matched. And we also want to learn the Gaussian noise here so that it's correctly estimate the true noise distribution. And we do this by just perform maximum likelihood estimation. However, we can see that this maximum likelihood estimation is intractable because of this log integral term. So, and as well as the log normalization term. So we overcome this issue by transforming these log integrals into variational lower bound using variational technique. Basically, we introduce variational distribution and then compute the variational lower bounds. And after some calculation, we can see that the variational lower bound that we obtain will also give the policy that we want. So this policy will maximizing this reward, and we will obtain the estimation of the optimal policy that used to generate the optimal action. So let's see the experimental result. So we evaluate Y on both artificial and real world datasets. And on both datasets, we see that Y yield improvement in the performance compared to prior method. So for this artificial data set with locomotion tasks on half cheetah and ant, we can see that y in red outperform other baseline method as shown in these two figures. We also use the real world data set collect using the crowdsourcing as shown in the previous example. And here we see that y in red, in the red line here, outperform other methods. So to summarize this part of y, you can see that y is robust against noisy demonstration when we appropriately choose the noise model. In this case, for the experiment, we use the Gaussian distribution as a noise, and it performed well on both artificial and real world dataset. So we also see that if you have the noise model, then it is easy to select worker that has low noise. So if we want to collect more data for this task, then we can select worker that has low noise to collect more data from them, because they tend to be expert. Now, the advantage of this work is that we still need to choose some good noise distribution. So on the left figure here, we rerun the experiment by generating the data that generate from Gaussian noise, and we can see that y perform very well in this task. However, on the right hand side here, we purposely generate data that use different kind of noise distribution, but we still use Gaussian noise for y, and we can see that in this particular setting, y perform very poorly because we purposely make the data distribution wrong. So we want to be able to have a more flexible method so that we don't have to choose different noise. And we do this by considering different assumption of the data. So as I mentioned, it's useful to model the noise, but it can be difficult to choose a good noise model. So in this work, which done by our intern in 2019, is to use a different assumption. Here we assume that the noisy state action distribution that we have denoted by P tilde is the mixture of expert state action distribution low E and non-expert state action distribution low N, with missing coefficient more than half. So the majority of the data that we have should be expert. And so the question is, given this kind of noisy demonstration from low tilde, can we learn the expert policy? In this work, we show that is possible. But first, let's try using standard divergence minimization such as GALE for this kind of mixture data. So we can see that in GALE, our goal is to minimize the Jensen-Shannon divergence between the data distribution that we observe, which is in this case P tilde, low tilde, and the data distribution of the generator, which is low pi. And by simple calculation, we can see that if we minimizing this divergence, we cannot learn the expert policy. Instead, we will learn the mixture of the expert data and non-expert data, as shown in this left figure, where we have bimodal data distribution with a mix of low E and low N. Now, if we have low pi and we match this low pi to low tilde, then we have this mixture distribution for low pi. So we cannot obtain the expert policy in this way. Now, our key idea to address this problem is to instead matching the mixture data to the mixture of the data. So basically, we match low tilde to low bar pi, where low bar prime is defined as in this equation. So it's the mixture between low pi and low N. And we can see in the bottom right figure that if we minimizing this Jensen-Shannon divergence, then we obtain the expert policy as a result. Because now the portion of the low N is matched by low N, and portion of the low E is matched by low prime. So now our goal is to solve this optimization problem, minimizing the Jensen-Shannon divergence. And following GANs or GALE, we use this discriminator to estimate the Jensen-Shannon divergence. However, we need to handle this extra term that we add, which is alpha and the expectation over low N. And in this work, we approximate these two quantities by using confidence score. So we define the confidence score as the value of the C of SA, which is the probability that this SA is drawn from the expert policy, drawn by the expert policy. So it is similar to the class posterior in the noisy level learning. So by using this confidence score, we obtain this semi-supervised learning method that can learn from unlabeled and unlabeled demonstration. So the label here means this demonstration is labeled by the confidence score. Whereas unlabeled is just demonstration that are not labeled. So it's just simply draw from low tilde. So for the unlabeled part, we basically use it to approximate this expectation, which correspond to the first term of this gestational divergence. While the second and third term correspond to these two terms that we add. So in the paper, we prove that this optimization problem give the consistent policy. So the result will be the expert policy. And we evaluate this method on locomotion benchmark tasks, where we artificially generate dataset. So 20% of the dataset are labeled by the confidence score. And this confidence score are obtained by some pre-trained classifier. And the rest of the rest of the demonstration are remain unlabeled. And from this figure, we can see a significant improvement of our method, which denote ICTL over AutoTL baseline. So in this figure, I also show another method that we propose in the paper called two-step importance-based imitation learning. So it also performed divergence minimization, but it used different technique to address the issue I mentioned. So for detail, please see the paper. So for the advantage and disadvantage of ICTL, it's clear that in ICTL we do not need to choose the noise distribution, so it overcomes the issue of why. Moreover, we can also utilize both unlabeled and labeled dataset in ICTL. So not all data needs to be labeled in this work. So thirdly, we also evaluate the robustness of ICTL against noisy confidence level, where we allow the confidence level to have some noise. So it doesn't need to be exactly correct. However, clearly the disadvantage of this work is that we still need experts to provide some confidence level. So without those, we cannot apply ICTL. Now we want to address this issue in this next work. So to address this issue, we change the perspective from divergence minimization to classification risk optimization. So there are many classification risks that we can use, but in this work, we focus on balance risk. So we define the balance risk of a binary classifier G as in this equation. So here P is the data distribution of a positive data, and N is a distribution of negative data, and L is a class-based loss function. So if we minimizing this risk function, then we obtain a binary classifier where we assume that the test data distribution has balance positive and negative. So the interesting thing is that for KL and ICKL, we can rewrite its optimization problem as balance risk optimization. So for KL, this is very straightforward because we know that GAN can be regarded as a method that optimizes binary cross entropy loss, and it's basically equivalent to this balance risk with logistic loss defined as this. So for ICTL, it's also simple because we can just replace this negative data density by this mixture and replace this positive data density by our noisy data distribution. Then we obtain ICTL. So this is an interesting point, but the important is how can we use this knowledge, right? So in this work, we use the knowledge of robust classification. So as Kang Sang mentioned in the previous presentation, classification with noisy label has been studied extensively in the past and also currently. And in this work, we will focus on the recent result of Children Pakdi et al. In 2019, which state that a classifier learned from noisy label data is identical to that learned from clean label data if we use the balance risk and asymmetric loss. So in the first line of this equation, we have that G star is the classifier that minimizes the clean risk. So P is just positive data and N just negative data. So this classifier will be equivalent to that obtained by minimizing this corrupt risk. So this is the corrupt positive class data distribution, and this is the corrupt negative data distribution, where we assume that alpha is larger than beta. So for this part, the positive data will be more than this part. And if we train a classifier by minimizing this risk, then we obtain the classifier that's identical to that obtained by the clean risk. So the important property is the symmetric loss. You state that the loss, the LS of set plus ls of minus z will be equal to some constant c. So the example of symmetric loss is shown in this right figure, where the sigmoid and unhinged normalized logistic and normalized hinge loss are symmetric, whereas the logistic loss as shown in this red line is not symmetric. So if you remember that Gale and ICTL does not use logistic loss, so it means that Gale and ICTL does not have this property that I show here. Now the main question is, if you have robust classification, can we use it for robust imitation? And the answer here is yes, we can. So the result is shown here in this archive paper. So I will state it informally here. So under the assumption that low prime of X equivalent to the mixture of the expert and non-expert state action distribution with mixing coefficient kappa prime, then the solution of this max bin optimization problem is consistent with the expert policy for any beta. So the beta is the coefficient here and here. Now, if we ignore the third term, and then just consider the first two terms, we can see that it's very similar to the gang objective or Gale objective, where we set beta equal to 1. However, we show that the third term is very important for robustness. We cannot just simply replace the logistic loss in Gale by symmetric loss and call it robust method, because it will not be robust. This is because the distribution, unlike in classification where we have a static data distribution, in imitation learning, the data distribution of low pi is changing during training, because now we are also maximizing over pi. So the class prior here will increase from 0 to 1 as we train. So we cannot just omit this third term and make it robust. So the detail is written in the paper. And so now we can solve imitation learning by optimizing this, but then how can we optimizing this, right? So for the first term, we can approximate the expectation by using our data that we obtain, the noisy demonstration that we obtain. So the second term, we can approximate this expectation by using the policy to collect data from the MTP. Now for the third term, we don't have the data from the non-expert policy, so we cannot really approximate this. However, we can use the property of robust classification as shown here, where the classification that we obtain by optimizing the corrupt loss, the corrupt list will be equivalent to the classifier we obtained by optimizing the clean list. So that means this G that we have can also classify between the expert data and non-expert data. So we can use this fact to perform pseudo labeling, where we randomly select data sample from the noisy demonstration and then label it using our classifier, and then choose the data sample that our classifier label as negative to approximate this expectation. So this means that we do not require label dataset, that the dataset that are labeled by the confidence to perform robust imitation learning. So this is a big improvement over ICTL. However, using this pseudo labeling can cause some issue because we basically use G to label the data and then use those data to train G again. So this can lead to some overconfidence prediction. So now we use the idea of co-learning and co-teaching to address this by training two classifiers and then exchange their pseudo labeling. So we call our method real code. So this is the experimental result that we did for real code. So we consider locomotion benchmark tasks using artificial dataset where we varying the noise rate. So the noise rate, the high noise rate means there are small amount of expert dataset. There are small amount of expert data samples. And we can see in this result that the real code method in red outperform other method, especially for high noise rate. So say if you have 0.4 noise rate, then we can see the clear improvement of real code over the standard Gale that use logistic loss, as well as Gale that use other symmetric loss. So it's clear that the advantage of real code is that we can learn from noisy demonstration without using label from expert. And this is a big improvement over ICTL that I mentioned. Also, I like where we have to choose some noise distribution and then estimate it. In real code, we do not need to choose noise distribution. We can simply give it noisy demonstration, then just let it run. We don't need to choose the noise distribution. However, the main advantage of this work is that the current result of the consistency only proven for the asymptotic setting. So we assume that we have the infinite data to approximate the to compute the expectation exactly, as well as we can solve the optimization to the global solution. So currently we don't know the behavior in the finite sample setting where we may have local solution or the approximation error. And so to summarize this talk, in this talk we discussed that learning from demonstration is an effective way to solve sequential decision making, which should be useful for artificial intelligence development. However, we should also take into account the possibility that the demonstration that we have are corrupt by noise. And so far, we have developed 3 methods to handle such noise in different ways. So in the first method, we use rational technique to estimate the reward function and the noise distribution, then learn the policy from those reward functions. In the second method, we develop divergence minimization algorithm that use confidence score to handle the noise. In the third work, we use classification risk to handle the noise. So that's all for my talk. This is the list of reference. I will answer the question. So how? So 3. Can we formulate the? So the first question is, can we formulate the solution to the noisy reward problem with the DINA framework, or do you think the nature of the problem is different? So yes, so in the DINA framework, we learn the transition probability using some data sample, right? And then we just run standard reinforcement learning algorithm on top of that. So in this imitation learning framework, the RL part does not matter. We can use either model free or model based. We don't care. We just need to have a reward function. So the answer to your question is yes, we can use DINA framework. So it's not different. So in the second question, in traditional classification, noisy level can cause overfit after some later epoch, assuming trending and we observe the same things as in IL with noisy reward. Overfit. Actually, I did not observe this because no. The answer is no. What we observe is rather the overfit to the policy. So we train the policy based on the reward, and during policy training, we add some exploration, add some noise to perform exploration. So actually, the overfitting does not cause much problem, as far as I observe. So very nice talk. What is the difference between diverse quality demonstration and noisy demonstration? So it's basically the same, but technically speaking, diverse quality demonstration assume that for each demonstration that we have, they have diverse quality. So one can be good, one can be bad. But for the noisy demonstration, we view it as for each state action pair, it can be noisy. That's the question. It's just trajectory centric or state action pair centric. Second question is why noise only exists in action instead of state. So this is because action is what the demonstrator can control. The demonstrator cannot control the state. The state is determined by the environment. So if we ask demonstrator to perform some action, the noise can only occur from the action that they execute. It cannot, or it cannot occur in the state. So if it occurs in the state, then it's the fault of the system, and we need different way to handle that. For example, we can use partial observable Markov vision process to handle those things. So it's different setting. Third, how to handle large scale state action pair. So I think the current work can already handle large scale state action pair because we use deep neural network, so it can scale very nicely to large scale problems. And by the way, can we do adversarial demonstration that mislead the IL model? So this is an interesting direction actually. So for the adversarial demonstration, we would assume that there are some demonstration that purposefully try to lead the Gen 2 different objective. And I think the current framework is already include those things as a non-expert part. But I'm not sure actually. I'm not sure if the current work can really handle this, but theoretically it should be able to handle adversarial demonstration, but we need to try, I think. Yes, so that's my answer. So I think that's all the question. Then
Okay, so thank you very much. Then let's move on to the last talk. So Shuo-chan, so can you share the screen?
Hi everyone, this is Shuo-Chen at Imperfect Information Learning Team. Let me introduce my research topic and some of our recent works. This talk will firstly give a brief introduction to the concept and application scenario of machine learning, and we also briefly review some representative works from two aspects. Those are the metric forms and the loss functions. Then we would like to investigate the main challenges of machine learning when the supervised information is inaccurate, and also the challenges when the data is with high dimensionality. Finally, we simply introduce our recent works on robust machine learning to deal with high dimensional data. First, let me talk about the problem setting and its downstream task. I think machine learning is an old but very classical and important problem in machine learning. Nowadays, it already has many application scenarios and being used for many downstream tasks. But before that, let's review the basic concept and definition of this learning task. So in machine learning, we aim to learn a distance function, dxz, to measure the similarity between data points x and z. This is actually a traditional supervised learning problem. So we are usually given a set of data pairs xi, zi, with the similarity label yi. In the common settings, the similarity labels can be directly annotated in some tasks such as person re-identification and face verification. But sometimes the similarity labels can also be generated from the class labels. During training phase, the learning algorithm will try to reduce the the distance between positive pairs of example, and meanwhile enlarge the distance between negative pairs of example. This is a very general, important, and widely used learning problem. Some quick example like face verification and image retrieval. In such recognition task, all you need is the distance calculation between two data examples. And generally speaking, the KNN-based classification and the K-means-based clustering actually focus on the distance calculation between two data points. And an effective distance function can be used to significantly improve the prediction accuracy. So, and some of us would also know about the few-shot learning or few-shot recognition, which is another application problem. So in few-shot learning, we can also directly use a learning metric to recognize samples from unseen class. So anyway, we can find that machine learning has been well applied in not only the traditional machine learning task, but also in some very hot topics. All right, now in the following slide, let's briefly review some representative works in machine learning. Firstly, we want to talk about the main forms of distance metrics. As I mentioned before, we aim to learn a distance function for such a learning task. So the first thing should be, how can we build a learnable distance function? The earliest distance function was published in Eric Xin's NeurIPS paper, which is also the earliest work in machine learning. Actually, this learning distance is a well-known Mahana-Norbis distance in statistics. Many years has passed, but this distance metric is still a welcome topic, and there are still some related papers published on SML and NeurIPS. This distance function has a very intuitive and simple interpretation. It directly considers to learn several linear transformation to separate the data in different projections, and the learning parameter is a matrix consists of all project consists of all projection vectors. When the data is nonlinear and has some manifold geometry, people consider to transform the original data from sample space to a manifold space. And the learning algorithm will learn a linear or squared function to measure the distance on a given manifold. But the main drawback of this type of method is that the manifold must be given in advance. So here the mapping relationship G must be given and known. So people sometimes think the usability of this type of nonlinear extension is somewhat limited. So in this case, a more general and a more popular and widely used machine learning form should be the deep neural network-based metric. But in fact, this is also a very simple extension from the original linear form. You can see the distance form in this equation. The extension from linear model to deep model is the introducing of the mapping W, which plays the role of feature extraction before the linear projection. So in this way, you can also regard the linear projection as a regular fully connected layer in neural networks. So people usually think this type of nonlinear extension is not really a new thing, but it's really a powerful way to and has achieved promising results in many recognition tasks such as classification, verification, retrieval, and also the field shot recognition, which I mentioned in the before slide. So most existing machine learning algorithms employs both three types of distance metric. There are also some other metric forms, but to the best of my knowledge, the most popular three forms are as I discussed in the previous three slides. Okay, based on the understanding of those three distance metric, and now all we need is how to design the loss function to train the model or learn the parameter of the distance function. And here I just simply show you some representative loss function in machine learning, and our recent work is also based on this. I'm not going to show the mathematical equation of the loss function, but just discuss the concept of the loss function by some figures. Here you can find two figures for contrastive loss and tributated loss. The earliest contrastive loss simply considers the pairwise data and build some loss evaluation for each pair of data example. The loss function will expect the large distance value for negative pairs, and meanwhile reducing the distance between positive pairs of example. In comparison to the classical contrastive loss, the tributated loss, or called relative similarity loss, does not target the pairwise data. Instead, it considers a tributated case to constrain a relative distance. That is, the negative pair distance should just be larger than the positive pair distance in a triplet. This practice actually lead to more data example. Suppose when you have n training examples, the sample size in contrast loss is n squared. But for the triplet loss, you will have a large n cube sample size. But this will be good for elevating the overfitting problem. And for more general cases, we also have many variants of tributated loss, such as n-pairs loss, rankly listed loss, and lifted structure embedding loss. We do not need to explain each of them in detail, but we can basically find the recent proposed loss function mainly focused on the relative similarity rather than the absolute similarities. So generally speaking, they usually consider a group of examples, which sometimes also be regarded as a mini batch in stochastic optimization. Then they set up different rules to constrain the distance between pairwise examples. And the main difference among them is just how to build up the group of examples. just how to build up the example, the groups. So just as the 4 figures showing in this slide. All right, the previous slide just simply introduce the concept, the downstream task, and the overall framework, and some important details of existing metrics learning methods. Now we can briefly investigate some challenges of metric learning in recent advance. And when the data is imperfect, it comes to 2 main situations. The first one is with inaccurate labels. Another is the data example itself to be corrupted. For the first type of challenge with inaccurate annotations, I think some problem settings are very similar to the traditional classifier learning, which is introduced and discussed by Dr. Gang Liu before us. But there are still some specific works regarding this weakly supervised metric learning problem, such as learning with label noise, learning with positive and unlabeled supervision, and learning with positive competent labels. So I think some of them are already done by the research scholar in our team at Lincoln AIPs. So I just list them here. The other type of challenge and problem setting in metric learning considers that the data example are with different noise or transformations. My previous works also focus on this problem setting, and these works are collaborated with my colleagues in the University of Pittsburgh, USA. But I'm not going to introduce the details of them. Besides the case of the imperfect data, metric learning can also have difficulties even though the data is complete. As you can see in this equation, when the data dimensionality approaches to infinity, a trouble is that all distance becomes the same value. That is the divergence between maximum distance and the minimum distance gradually converge to 0. It means that the distance in the high dimensional space will lose its discriminability. So, and some recent work, including here the AAI 2015 and NeurIPS 2019, also reveals that the dimensionality reduction techniques cannot always work well for metric learning tasks, because sometimes the reduced dimensionalities can still be very high. Otherwise, some important features cannot be preserved. So recently we have this work to explore the distance distribution in the high dimensional space. We firstly consider to unify the existing metric as I introduced in the previous slides by denoting here an abstract valued vector valued function phi x. We have this general form to summarize existing 3 types of distance metrics, that is linear form, manifold-based form, and deep neural network-based form. Then we consider the distribution of this unified distance under this independent non-identically distributed assumption. By using the central limit theorem, we find that this unified distance metric defined in the previous slide will approximately be the norm distribution in the high dimensional space. Based on such important result, we also explored the error bound of the false positive rate, and we find that the error bound, the upper bound will mainly dependent on a monotone increasing function. So it means that the error bound will be consistently enlarged with the increasing of the metric space boundary. However, for conventional machine learning algorithms, the problem is that the metric space boundary is usually unbounded. So this just inspires us to construct a new boundary restricted metric. I would like to use this figure to intuitively describe the framework of our proposed boundary restricted metric. Our main contribution is the introducing of the dash box, where the restriction function is used to constrain the divergence between 2 data points in each project directions. Here is a mathematical definition of our proposed boundary restricted metric. And this figure is a visualization of our introduced restricted function. Briefly speaking, the divergence in each project direction will gradually converge to an upper bound by this restriction way. When we employ such a boundary restricted function, the metric space would change from the left to the right. And the negative pair distance will never freely vary in a bounded space. And under the same margin setting, data points in our in our boundary restricted metric space will have a better separability. Here are just some mathematical details for building the loss function and the optimization algorithm. We are not explaining them, but I show you a very interesting analysis result during the training phase. Let's see the gradient result of loss function equipped with our proposed boundary restricted metric. We can find that introducing the restrict function will just append an additional term in the gradient. And this appended term will converge to 0 for some extremely large distance value. And then the gradient will also converge to 0 and stop the iteration. So from the gradient analysis, we may also clearly see how does the function R restrict the metric space. Then when we use the SGD to solve the learning objectives, we have this convergence rate. But this conclusion of convergence rate can be directly inherited from SGD algorithm. So I think this is a simple and trivial result. Let me show you some new theoretical result and experimental result for our proposed method. Firstly, we can prove that our proposed distance function is topologically defined metric, so its geometric soundness can be guaranteed. The two conclusions in theorem 2 have very similar condition with linear Mahalanobis distance case. So this can be regarded as a natural nonlinear extension for the linear model. Secondly, we can also reveal that although the metric space is restricted, the fitting capability of the learning algorithm does not really sacrificed. For the generalization error bound, we also have a corresponding conclusion. Please see the function theta b here in the right hand of this equality. This function is monotone increasing with respect to the metric space boundary B. So it means that when we restrict the metric space boundary, the generalization error bound will also be shrunk and reduced. Then we also have some experimental result to validate the effectiveness of our method. This is a toy data example. The four classes of points can be separated by both two methods in their training phase. However, our method obtain have a more balanced separation, and all inter-class distance are comparable in figure B. And accordingly, its distance histogram in the test phase is more accurate as shown in figure D. Here are some experiment results on real-world data. We have experiments on both linear and deep model. The experiments on linear model are classification results, and the experiments on deep model are verification results. We can find that our proposed new new distance metric can work well in both two cases, two model settings. Here are experiments on a noisy data set. We crop the MNIST data set by Gaussian noise on both training and test data, and observe that the classification accuracy of all compared methods. Here the last two terms are our method. Our error rates are significantly lower than other methods under this noise condition. So this result just clearly validated the robustness of this method. Finally, let's give a simple summary. So in this talk, we briefly review some classical works of machine learning. Then we investigate the error bound of false positive rate of existing method in high dimensional space. Then a new error bound. Then this new error bound just inspire us to build a new boundary restricted metric to restrict the FPR value of conventional method. And finally, we also demonstrated the effectiveness of our method by theoretical results and as well as experimental results. All right, that's all my report. Thanks. Okay, let me check if you have any question in the Q&A chatting box. What's the difference between manifold-based metric and the end? Oh, I think the difference is manifold-based metric is still basically a linear method. Its learning parameter is still a matrix, but not a network weights, just like a deep neural network-based metric. So I think the main difference is one thing is linear, another is nonlinear. Yeah.
All right, then, thank you very much. So let me conclude. So thank you very much for joining the seminar today. So this is actually the 7th round of the seminar series. And this is the last seminar in this year. But after 2 weeks, from January 13th, we have new seminar series. So every week. And actually, we have more than 40 teams in RIC and AIP, and this is still the 7th seminar. So this means we still have more than 30 seminars in the coming year. So if you are interested and if you have time, please join the seminars. And also for the previous seminars, already so videos are on the web. So if you are interested in the previous seminars, please take a look at the web page and you can see some videos here. And also we will update our seminar today on the web. If you missed some information, you can also see the video. But of course, we are happy to have email from you and have more discussion. So our team is always looking for good collaborators of course machine learning or more pure mathematics people and also applied people. So we are also interested in using our machine learning techniques in solving real world problems. So we are happy to have more discussion with all of you. So thank you very much for joining us today. And I had some comments in the chat window. Okay, so that's not them. Okay, then, so this is the end of the seminar today. So I think this year was really challenging. So we had COVID-19 and our life was really changed. Hope that next year will be a really bright year and hope that you have nice and safe Christmas and New Year. Thank you very much. Bye-bye.